Okay, hello everyone. I think last time for the differentiation rule, we discussed the product rule. So I just want to show you some perspective on how to see this product rule. So imagine you have some sort of rectangle which has u and v as sides. And imagine that you are going to increase. You're going to increase the size. You're going to increase, let's say, some delta u and some delta v. And of course, for those increases, we can imagine how it's going to be for each area that is increasing. Okay, this part and this part is all increased because of this delta and this delta. Okay. Now we can configure this and then rewrite our change of area of the rectangle. Let me make it a little bit bigger. So let me put over here, maybe a little bit smaller here, and then focus now on this part. Okay. Now if we see, okay, the change, the area of the rectangle is going to be all the addition of this shaded area, right? Okay. So we have the u delta v, v delta u, and delta u delta v. Okay. And now we define all these terms by delta x. If you have the textbook, you can look on the textbook. This is exactly the same. So define with the delta x. Okay. And then, as usual, every time we deal with derivative or later with the integration, we are always dealing with getting limit. So we take the limit and make sure that this delta x getting closer to 0. So it's getting smaller and smaller, and take the delta x closer to 0. Then we have this expression. Okay, we have this expression, and all this we are going to be taken by this limit. Okay. So we're going to compute the limit. We're going to compute the limit, and we see that every let's say u and v like a function. Okay? So they have their own function. So let's say u is here. Its state is a function, but it multiplies with the limit of the change, okay, of the change of this delta v with respect to this delta x. Okay? It's also the same, and then at the end we have these two limits. Okay? And of course, the last part here, when x is getting 0, they both are getting 0. So we can, and of course this delta is getting 0, so we are getting the 0 situation over here. Which means that the final result is what we have in the product rule. And remember, in my class, if you think that maybe it doesn't really necessary to be take notes, you don't need to take notes. Please just write something that you think it's important. Okay? You think it's important. All the class notes, I will, after some time, maybe after 2 meetings or 3 meetings, I will put in the Moodle. Okay? For example, like last time, I have put the chapter 1, chapter 2. You can review the notes that I made. Maybe if you see something that is, maybe you need to make sure which part that you need to take care. Then you can ask me those questions. Okay? But for something like this, I think it's up to you. If you want to take notes, that's okay. If not, then it's also okay. Okay. But what I want to remember you to at least realize is we have this pattern here, which this is going to be. So every time you have a function like f or g, you have 2 functions, you are going to multiply these 2 functions, and at the same time, you are going to derive these 2 functions. So when you are deriving these 2 functions, you are going to apply these rules, okay, all the time. But of course, this is going to be the single variable, okay? Single variable. So both are function of x. If they are different variables, we need to take another calculus. It's calculus 2. For multivariable. In calculus 1, we only deal with variable x, only one, okay, one variable, okay? Because we have like multi-variable that will be calculus too. Okay, that's the product rule, okay? So at the end, where's the, let me make it bigger. So at the end, of course, we need to set our requirement. F and G differentiable. Okay, differentiable. I hope you still understand the differentiable. It means that you can derive at that point. It has the tangent or the slope at that point. If it is a pointy corner or if it is having any discontinuity, of course you cannot derive. It doesn't. You cannot differentiate at that point, right? Okay, so if f g differentiable, then this can be opposed. Okay, so that's product rule. Okay, the next part is the quotient rule. Okay, the quotient rule. I hope you can maybe summarize this into just one single statement. The last one, I think that will be very. I think already summarized everything around. Okay? Like if you need more like understanding in a more conceptual like proof, maybe I will add something maybe later if I have time. Okay, but for now, I think we can just take the product rule as the summary. Okay, and the quotient rule. Okay, the quotient rule. So I think our approach is similar. So we take the un over v now, and then we are getting some additional length, which we define as the delta. So the delta u and then delta v, which means that these terms, they are going to have differences, right? So we set up this statement first that we need to understand, which means that it is going to be the whole thing altogether minus the original one. This is the original one. So we want to know how much delta between the u over v. So we could set up, we have some plus delta, then we need to minus with the original value or function. We think u and v as a function. And then we set up some simplification, we combine these two together, we get this expression. And now, to get this delta into our limit definition and make it into differentiation, again, the same concept. Every time we see terms, derivative, differentiation, it is about limit. Okay? So we take limit as some delta will approach 0. So here's the delta x. Okay? We set the delta x because that is our concern. Okay? That is our variable. Okay? So delta x closer to 0. So we can set up the delta u over v over delta x. Okay? And we set up this closer to 0. And everything up here is getting defined by the delta x. Okay? They are getting defined by delta x. And then we get the statement here that as we getting closer, to delta x getting to 0, our delta v also getting to 0. And then because v is differentiable and continuous, and then we can use the limit law, and we get this expression, which we can define this limit becomes this d dx or du dx. Okay? So every time you see like proving statement in mathematics, you see delta and then they put limit, and the result usually they write d. So you can think if anything in mathematics you see d dx or d something, it means that is going to be really small. It's going to be really small. That is affected by the limit because they are getting closer, and we need to make statement. Okay, this is very small. How to make it very small? Usually you write with d, or in the partial, when you learn partial, we write the Leibniz notation. But usually d, okay, for just a single variable derivative, we usually use d. So it's reflected that okay, the implication is we can write as d dx of u, meaning this statement means that the first derivative of u with respect to x. Okay? So we differentiate in terms of the variable x. Okay? So usually we write d dx here. Or sometimes we can put the accent or prime. So sometimes, for example, you can also write this as u prime or is phi prime. Okay. To make it more easy to look at. But this u prime means the first derivative of u. And in this case, because we differentiate with respect to x, we say this is the first derivative with respect to x of this u. Okay, we call this u prime or b prime. And all the way here, the delta v is going to be 0. And we are going to multiply this v and v, so we get v squared. Okay, so at the end, let me put some conclusion here. You get these expressions, okay? I have some suggestion on how to apply all of this. If you think that this is too much, if you see the product rule and the quotient rule, they have patterns, right? They have patterns. Let me write patterns here. So usually I write for product rule. Let's say we have d dx of the fg as our function fg. If the product rule, let's say f prime g plus g prime f. I initially write in order like this. So that when you take the quotient rule, what you need to do is, let me write here. You write the same thing, but minus. And then over g squared. Okay? Just some suggestions. Okay? So that you can see that both are actually have similar patterns. Okay? But there's difference in the value, positive and negative. Okay.
Can you send the notes later on?
Okay.
Also send the one where we need to find the derivative with triggers.
Oh, okay.
Yeah, it's no problem.
Every chapter 3. Okay, so that's product rule, quotient rule. If you find this helpful, okay, you can write this. But if you want to write in the more direct, like the textbook, it's okay too. They're the same thing. It's the same thing. So, using these two rules, every time you see any function, and you know the function can be separated, it becomes two. Either you can multiply both functions, or it is you can divide by these two functions. Then you can apply both of these rules. Okay. The next thing that I suggest is to give you like more practice to see if you see any function, because of course in calculus you are not only learning the calculus part, but all the process inside, like the algebra, any mathematical notations, the basic mathematics as well. Okay, so not only this calculus part. Okay. Okay, some table of differentiation formulas. Okay. Have I explained about the exponent? I forgot. Have I explained? Not yet, right? Okay. Okay, let me mark this as not yet. But perhaps we are going to discuss about that first. Okay, now we are going to discuss this exponent. Okay. Okay, I will move to the next page. So exponent or exponential functions. Suppose we have f of x equal a b with power of x. Let's say b is any numbers, or we call it base. And usually if we express in exponential with any numbers as a constant, we usually write as b. Okay? So let's say we have this. We would like to know the derivative of this. Okay? So let's start with the definitions. So just take all the step here. Let me just write the original one, the original expression for limit definition. Oh, by the way, some of you haven't taken the quiz results here. I think later I will give you. Okay. And then we have this. Okay. Okay. We exchange all the x plus h and x with the function b with power of x. And then what's happened now is we take factor b with power of x, and we see that this is going to be this over h, right? And then we can write, because we take limit for this h, and b is a constant, and x is nothing that we are going to consider as limit, and we can take this outside, right? Okay, and we can concentrate on this one on the right side. So let's do that. Okay? So let's take out the b. So let's write f prime x. And then we can write limit. Okay, now we have this expression. Now the problem is we need to make some definition on this limit. Okay? But before we define the limit, if we take x equal to 0, let's say this is 0 here, we put 0, what's happened? This is a number with power of 0. It becomes 1. So actually this part is f derivative at x equals 0, right? Okay, so we can write at x equals 0, f prime 0 becomes limit okay. So it seems that we can make some conclusion that if we take f prime x, then this will result in f prime 0 multiplied with the b with power of x. Okay. At least this is conclusion for now. Okay. And then what can we do? Okay, what can we do? Now of course, b Can be any number. Okay? Now to make it simple, let's just make some trial and error. Just make trial and error. So from these expressions, from this one here, we try some b. Okay, try some b. And then to make it obvious, let's just say we take b equal 2 and b equal 3. Or maybe let's write b equal 2 first. So when b equal 2, the f prime 0 becomes 2 and how about the h? H, we can start with 0.1, 0.01, like we did in limit before. We try some numbers that is really, really small and getting close to 0. And then we take, okay, check h equals 0.1 or 0.01 or even 0.001. Okay. And you will see that our limit is approximating around 693. Okay. When we are take h getting lower and lower and lower, it seems that it's going to approximate this number. Okay? It's approximate this number. And then try b equal 3. So this is the first, and the second one, try b equal 3. Okay, and then the same thing, check h, maybe start from 0.1, 0.01, and 0.001. Okay, check all that h. It means that if you are bring any calculator, you can check by yourself. 3 input power with 0. Let's say we try 0.01. 3 with power of 0.01, you get some results. Minus 1, some numbers, and then divide by this 0.01. Can you try? Anyone bring calculator? Okay. Yeah, 1.104. 1.1. So if you check using 0.01, 4, right?
104.
Oh, 104. Sorry. Okay. And I believe if you are getting closer to 0, maybe take more digits behind the decimals, you will see that I think it's going to be 0.09. I think 0.09. So it's getting closer to 0.09. So, but I think this is still okay. So between these 2 and 3, for sure, you will see the number because it's in between 0.6 and 1.1. At some point, at some b, it will equal to 1. That is e. When b is equal to e, the result is exactly 1. Okay? So e, let me write here, maybe write on the left. So e is the number such that we take limit okay. Now since it's equal 1, whenever we have a function of e with power of x, we derive, it's the same thing as it is. Okay? So we're right here. So the formula is f prime 0, and then this will be b to the power of x. Okay? So when B equal E, then this will be and this f prime 0 is 1. So let me write here, if f of x is e with power of x, then f prime x is, okay. It's so simple, but how we get that is actually, I think, quite interesting. Sometimes we call E, you know E? What's that about? Why we call this E? Why not? I mean, yeah, Euler, the founder, Euler. Okay, if you forget that. And usually you can see E in most of the exponential phenomena, like in population, like growth. Even in economics, finance, you can see the E. In some models for physics, chemistry, chemical, populations, I think you will find a lot of application of E. So, but what's happened if we have, for example, if let me make a rectangle first to make sure that this is okay. And what happened if I take, for example, 2 with power of x? So if I take 2 with power of x, what is the first derivative? Remember that you have the f prime of 0 multiply with b, that's up there. B with power of x. So if b is 2, then the first derivative, what is the f prime 0? The f prime 0 is the one that we calculate on the right side. This one. It's 0.693 something. Okay. And then this is for the number b of equal to 3. Okay. So if we take b equal to 2, then we have, this is going to be, we can write for now, we can write like this. And then do 2 power of x. But it's not really convenient, right, if we write a number. But what is this numbers actually? This is the ln, okay? This is actually ln 2. So you can think, aside from e, whenever you have like something like a constant with power of x, you derive. It means you will see the function itself multiply the logarithmic natural of that number. It can be 2, 3, 4. Okay? So we can write here the okay. So this is the conclusion. So we have the definition of E, at least. Also, if you want to look at the graphs, how the exponent looks like. We can also check. For example, I forgot to put the graph here, but let me just draw for you. Okay. Okay, let's say we have one over there. Oh, maybe not. Maybe here. Oh. Okay, let's say that is the 2 power x, and then we have, let's say this is the 3, and the e is in between. Or maybe this is going to be a little bit going to the left, okay, like that. Oh. Let's say that is the e, because it's getting closer to 3, right? So this will be y equal e to the x. Okay. And all the graphs, they will crossing this point, okay, when y equal 1. I think we can see that when x equals 0, they are going to be 1, right? With power of 0. So they are going to be 1 here. Okay, so exponent. So we have the, I think, the very basic definition for derivatives, the product rule, the quotient rule, the exponent, the e. So I think today's more theory. Okay, I hope on Thursday class I can provide you with more exercise. I think your TA also will provide you with some exercise. Okay, now let's continue a little bit. Okay. So we take, it's not trigonometric, sorry. Should be trigonometric function. Okay, as usual, okay, this is just a regular graph of sine x. Okay. I hope you know how to draw this easily. Anyone still not get it? The Sine X? Let me know. Okay, 1, 2. Who else? Not really sure about this. What kind of graph is this? 3. Anyone? Okay. No, I'm just asking the Sine X. Okay. Now, for those of you who are not familiar, can you know the special angle or value for sine? What is sine 0? Yes, 0. What is it? Okay. Okay. I hope you can catch all the context. Okay. But basically, what we did here is we take some angle, from 0 and then maybe some angles in between, and then pi over 2, pi, and 2 pi. So in short, we can take those values between -1 and 1 because they are oscillated. So from -1 to 1, and then they are going to have some sort of, we call this, they have some periods. Okay? They have some periods. Okay? I think you will learn also in physics. We call this the amplitude. So for some periods, for example, for every 2 pi, they will have how many full waves, how many waves they will have. You learn in physics, right? But basically, the whole thing here is a function of sine x. Okay? This is a function of sine x. The blue one, okay? The red one is the slope. Okay? Remember the slope? The slope is actually every line, straight line, at every observed point. So if we observe maybe here, which means that at this angle here, okay, this is going to be horizontal. Okay. For example, pi over 2 is going to be here, and it's horizontal. Horizontal means the slope is 0, right? Okay. Now, if we could predict, okay, and if we connect all the small slope in every point, okay, so if we can connect all the small slope and then we could predict how it look like for the first derivative. Okay. Every time we do that, we start from slope equals 0 to make it easy. Okay. So this slope 0, and then we draw the f prime. It means at the slope 0, they are going to be crossing this x-axis. Okay, so let's see what's happened. Okay, at pi over 2, okay, it's crossing this. Right? And at this one here, minus pi over 2, it's also crossing. And now, how do we make sure that this is correct? So we could think that the slope here is getting positive. So all the way from this point, negative pi over 2 until pi over 2, it's positive. But how positive? You could maybe let me add one more, or maybe 2 lines to make it easy. Let me add green color. So let me add here and here. So from 0, it's positive, but then at some certain point, it's decreased, but still positive, right? It's still positive. So it's decreased from positive to 0. So you could sense that at this moment here, it could go up and down. You get the logic? You get the logic? Okay. So that's why we have this part here. Okay. And then do the same thing with the other interval, and you will see that now it's actually this is the curve for the cosine. Yes, correct. So this is actually the graph for the cosine x. We can write this is y equal cosine x, right? So you can see some sort of connections between sine and cosine, and you will see later. We can also prove how to derive sine and becoming cosine with some differentiation definition that we did before using limit. So it seems sort of like some of you maybe know, okay, the derivative of sine is cosine, but how and why, right? So let's go to that concept first, okay? So let's write that the f prime. So every time we need to prove something, we need to show that this is true. So let's write the original limit definition first. Write that we are going to take this sine, okay, sine x. So change all the function with sine. Now what's happened now? Now this is again, you need some extra effort if you are not really much knowing about trigonometry. So we have some x plus h inside here. We need to expand. And if you are still confused about how this trigonometry works, that is your homework, okay? For those of you who are not getting this trigonometry. I will also provide you in basic math, but for now, you need to catch up by yourself first. Okay? So sine x plus h is actually, let me write with the green one, that if we have this a plus b for that, this is sine a cosine b plus cosine a sine b. Okay. So let's write that down to here. So sine x and then cosine h and then plus cosine x and then sine h and then minus sine x. Okay, we are going to have a break and we can continue after that. Okay, now, okay, what's next here? Okay, what's next is I will group this sine x and cos h, this one and this one. I will group and write like that. Okay, and the other group will be, let me write with that bracket and plus cosine x sine h. Okay. Okay, and then I think we can factorize this part. So we have cosine h minus 1 over h. And then plus, let me write the limit separate from the equations. That this will be cosine x. And then we write sine h over h. Okay, let's stop for a while, because if we are not knowing anything about this limit, the sine h over h and then the cos h minus 1 over h, then we are not able to define the trigonometric function. So we need to take some time to prove what will be the result of these two limits. Okay? So let's say we start from here. Okay, we start from here, and how to prove this? We can start the proofing first is look at the graph. Okay, that's the very basic thing that we can take. Look at the graph of the, let's say we have the graph of f of x sine x over x. Okay. If you are input this function in your graphics either platform or website, you will see that at x equals 0, it's undefined, but it will be, if we take the limit, it will be getting closer to 1. Or you could say, if you use limit, it will be getting 1. Okay. But of course, that is from just see the graphs, like how visuals, from visuals. But we need more proof. Right? So the best way to check this, and taking the limit as the equal to 0 and closer to 0, is from geometry. Okay, from geometry. So let's try to assume some geometrical perspectives. So first is, first is, imagine that we have a circle. Okay. And then we can split the circle like making a pizza like this, like a slice of pizza. Okay. And then we could also take some polygons that is coincides with the circle. For example, I will take this polygons here, the side, this one side here, and then another side is there. And you can also see the polygons. We can also measure when it is getting closer to 0, it will also getting close to circle. I think I may not making it in a perfect proportion, but hopefully we can focus on the triangle. Okay? I think it's not perfect, okay. But that's okay. So this is O, this is A, this is B, and this is E. Okay. And then we have an angle that is in between OB and OA. So this is our angle. Okay, now if I'm asking what is the arc of AB? Okay, maybe assumption first. Assume this is a circle with center O and then central angle theta and radius is 1. Okay. So that's the assumption. And then if we take the circle and measure the distance between A and B, the arc, not the straight line, the arc, how do you measure? How do you measure? Can you measure the circle perimeter? What is that? 2 pi r, right? 2 pi r, okay? And then, if we know the angle, we know the ratio, this angle. Compare with the full circle. What is the full circle? 2 pi, right? So, we get theta over 2 pi. Okay. And r is equal 1. So the arc AB is just theta. Okay. Okay. Make sense? Okay. So that's arc AB.
And now we are going to see that actually if we take times
To check the length, okay, for sure, based on this geometric perspective, the length of arc AB is less than AE plus EB. Okay?
So let me write over here that the arc arc AB is less than AE plus EB. Okay. Now let's zoom in the triangle. Okay, let's zoom in the triangle while taking the
It's actually straight line like that. But
let me show you what it should be. Okay, what it should be. So let's take this triangle and zoom in. Okay. So this is the one that we are having.
the radius is 1. And this is the one pizza portion, right? One slice pizza portion. We have angle theta. Okay. And then let's say we are going to name some point. Okay? So we already named A, E, B. Okay. And then adding point C and point B. Point C is making another triangle here, which is another right triangle. Okay. And then this D is making another like big triangle. Okay. So we have at least 2 triangles that need to be observed. The triangle OCB and OAD. Okay, we have 2 triangles. Now, and what we are going to do next?
Next thing is observe triangle OAD. Okay. What is the tangent theta from the OAD?
Tangent theta is AD over OA, right? Or AO.
Okay. So we can write AD. Okay. So we can rewrite the AD as OA tangent theta. What is OA?
In the center, yeah, this is a circle. If the radius is 1, what is OA? Yeah, same 1. This is the radius, right? Yeah, radius, the same with this, right? Okay, so I can write AD is this tangent theta. Okay,
So let me write here that OA is the radius is 1. So AD is tangent theta. Okay, also
observe the line AB and the arc AB. Okay? So observe that.
So let's observe that the line AB
In terms of geometry, this will be less than the arc, right? Okay, let's write.
down here less than arc AB. And then
Because this is, you can see also this is another right triangle here, right? Then we know that the BC is less than the hypotenuse, right? The
AB. So we can write that this BC is less. Okay. So
If we look the triangle OBC, okay, triangle OBC, what is sine theta? Is BC over 1. One could say BC is sine. Okay, so we can exchange the sign. Okay. What is arc AB? Is theta from before, right? From our arc measurement. So sine theta should be less than theta. Okay.
okay, now let me write, maybe to give you more context how we got this. Let me write that the sine, or maybe from triangle OBC, the sine theta is BC over OB. Now we can see also that we are going to combine this
Two conclusions from the AB equal tangent theta and then this conclusion. So we have arc AB. We have
arc AB. Now we can say the arc AB is less than AE plus EB, or we can write directly AE plus ED, and we can rewrite this as just AD. So theta is less than sine theta over cosine theta. This is from the tangent. So we have sine theta less than theta. And then we have theta that less than sine theta over cosine theta. And what will we do from this one?
three functions, one in between. What we can do? Take the squeeze theorem.
We take the squeeze theorem. But let me rewrite divide by sine. So let me divide by sine. Let me divide by sine. So this will be 1. This will be theta over sine. And this will be 1 over cosine. But then let's rewrite reciprocal. So 1 over x becomes x. So theta over sine theta becomes sine theta over theta. It means that we are going to write like this. Okay? Okay, and then take the limit.
Okay, limit on the left, 1. Limit on the right, 1. So take the limit on the middle 1 is equal 1. Okay?
So by squeeze theorem. This is one proof. I have a second one that to prove this, still using geometry. This is, we use the distance, the length. We can prove using the area, the sector, and we find the area of the sector. That's, I think, easier to see, Okay. And this result is really, really important. Because if maybe you have, if you know the L'Hopital rule, okay, you can think, oh, we can use L'Hopital rule. Just become cosine theta, become 1, or cosine theta, 0, 1, right? But in the process, it's actually wrong. Why do you think it's wrong? Because it is, how to say, let me explain. This is by itself is definition. And L'Hopital rule is using derivative, which definition is this. So it's like, you cannot do that. Because this is already in definition. L'Hopital rule, you derive the top, derive the bottom. You use derivative, right? But the derivative itself for trigonometry, definition is this. So you cannot do that. Okay? You cannot use L'Hopital rule for this kind of situations. If you know the L'Hopital rule. For those who are wondering what is L'Hopital rule, we are going to see, I think, in the next few chapters. Okay, let me give you another another way to prove this. So let me take this as a copy. And hopefully I can finish by the time. Okay, let's say we still have the same assumptions using r equal 1 and then this triangle still the same. Okay, now observe the triangle OAB. So OAB is like this, right? Or maybe making what more ideal like that. This is C, B, O, A. Okay, we know that this will be a theta, and from the previous conclusion, the BC is our sine, so we can write sine theta here. This is 1, right? So the area of the triangle OAB, let me write area of triangle is half multiplied with what? Base, right? And then height, okay? In this case, half, what is the base? It's OA, right? And then BC, right? What is OA? It's the radius. So half, radius is 1, right? So radius is 1. So OA is radius. BC is sine. So it's sine theta. So this is area for, or maybe let me write area for OAB. Okay. And now observe triangle OAD. The big triangle, okay, the big triangle. Okay. And then we know that this is theta. This is O, A, D. And the AD is the tangent, right? Tangent theta. OA is 1. And again, the area, we can know that from the base is 1, so OA and AD. So area of OAD is half tangent theta. Okay, now we have two triangles in between. Now in between, we have the sector, the area of the pizza, okay, the slice of one pizza. Okay. And then the third one, let me write here, observe sector OAB, which means that we are going to have this and this, okay, and then basically one slice pizza. Okay. This is the theta. We have OA, and this is B, right? What is the area for the sector? Okay, you do the same thing. What is area of circle? Pi r squared. And doing the same thing using the theta over the whole circle 2 pi multiplied with the area of circle. Okay. So we take the area is theta over 2 pi multiplied with pi r squared, which is cancel, and r is just 1, so it will be half theta. Okay. Okay, now we have 3 components, and we can use the squeeze theorem, the same as previous one. So area of OAB, of course, this will be less than the sector OAB, and it's also less than the area of OAD. So OAB is sine theta over 2. Sector OAB is half theta. OAD is tangent theta over 2. Let's cancel all the 2. And then let's divide with sine. So this will be 1 less theta less 1 over cos. Oh, theta over sine, sorry. This will be 1 over cos. And doing the same thing with reciprocal. So we change this into 1, or maybe cosine theta is less than sine theta over theta less than 1. And then the same, take the limit, and take the limit. Okay, and then by squeeze theorem, you will get that sine theta over theta is equal to 1 when limit x or theta equal to 0 or approaching 0. Okay. Oh, either way, you can prove. I think in the textbook, I think they only mentioned the first one. I give you the second one to give you more visuals to see that we can also prove this using the area. Okay. Let me make this a little bit smaller. I will write too large. Make it a little bit small, maybe like that. And maybe let me write conclusion in here. So limit as, let me use x of sine x over x is equal 1. Okay. Usually, this limit, sine x over x, will also relate to this limit, okay, that we can also prove. So based on what we have here, then we can
try to restructure this, find in some way that we can also involve this sine x over x inside this. How to do that? The first thing is you need to remember the very basic in trigonometric identity, which is sine squared plus cosine squared is equal to 1. Now we have 1 minus cosine, but it's not squared. So if we want to make this into 1 minus cosine squared, we're going to multiply with what? 1 plus, right? 1 plus cosine squared. So let's multiply with that.
Okay. So multiply with this. Don't forget that you need to also include this. Okay, to make sure that it's in balance. A is like A minus B, A plus B. We have A squared minus B squared. So we have 1 minus cosine squared if we multiply it. So let's write this. And just keep as it is.
Now we have 1 minus cosine squared, which is sine squared. Okay? We can exchange this with sine squared. Okay? But what's next? Sine squared means sine x multiplied with sine x. How about we separate them? Okay. So we take the limit sine x over x at the left and the limit sine x over this 1 plus cosine x. Okay? Okay, we know the left one is 1 from our definition, but how about this one? We put x at 0, it's 0 over 1. So the whole thing on the right will be 0. So the conclusion 0 and then 1 will be 0. Okay, will be 0. Okay, now we are going to use the sine x over x and then sine x over 1 plus cosine x in our
Definition for derivative, okay?
And I think this kind of help you in some way for some specific limit question. For example,
let's say we have limit sine 6x over 3x, or maybe 5x,
Any idea? The shortcut is equal to 6 over 5. But how do we get it? Remember, we need to make sure that this x is equal with this x. So we need to multiply with 6x over here, right? Okay.
So we need to make sure that we have, let me write here, sine 6x over 6x, right? So we need to multiply this with 6 over 5, right? Correct? Okay.
Okay. This one, if you take limit, is equal 1. So the answer will be 6 over 5. You get it?
So take limit. So this whole thing here is equal 1. So this will be equal to 6 over 5. So this will be 6 over 5.
Okay.
Okay, let me copy some parts from the previous one that we did. This one. Let me copy again this part. And that's right here. Okay. Okay, now we can deal with this.
Now with our previous conclusions, the limit for sine h over h, this will become 1. And for this one will be 0. So the f prime will be equal to cosine x. Okay.
So this will be equal to 0. This will be equal to 1. So the f prime x or this f prime x is
Okay, that's the conclusion. So if in previous maybe you already know, like, okay, derivative of sine is cosine. But now you know how do we get the cosine? Maybe sometimes maybe your younger brother or sister would like to ask to you, and you can practice by yourself. Okay, I can help you to understand this one. Maybe but at least in our course, as long as you know the logic, reasoning, and how to apply the derivatives, it should be okay. No need to memorize everything. I think in the previous one it's 1 minus, but the results are the same. You can try the limit also. You can try. Crazy. Okay, before we end, I would like to just introduce you the last one for today's. Will be the chain rule. The chain rule. So I think today we have the product rule, quotient rule, the trigonometric exponent, and the last thing is chain rule. So I will all the most theory for the differentiation techniques for today's part, and we can review Thursday. Okay, also your TA also will review, and you will have more exercise.
okay. The last part for today, the chain rule. Let me just give you this first. Okay, if too much words, I will explain.
I think I will explain below. But let's see that we have f, or let me rewrite the
Important words. Okay,
I think more words like this makes you confused, right? But let me summarize.
okay, let me summarize. Okay, so we have let's write the big F is FOG.
It's the composite. Composite. We combine f with g, so it means that the function g is inside this function f. Or we could write
This as And then somehow, if you would like to derive this, okay, which means that we are going to derive the whole thing. So how do we do that? So we have this, and then multiply the derivative of the inside, which is g prime x. So before I'm showing you some proof, let me just reviewing how we are going to use this chain rule. Okay. So if, okay, example, okay, let me write example here. If we have f of x like that, is, let's start from this one first. X squared plus 1, suppose that. And then we would like to know the derivative. What would be? Okay, what will be? The first thing is, look at this function. You can think this function is, I have something inside. For example, it's x plus 1. So if I make this into separate functions, let's imagine that if this f is f of g, like that, and if g is x squared plus 1, and f is just square root of x, okay? We could see that this function is actually g is x squared plus 1, and then we put the inside of this square root. Okay? You could think something like you have the outside function, which is the square root of x, and the inside function, which is the x squared plus 1. The steps that you are going to do is, you are going to derive the outside function first, which is the square root of x. You derive this, become 1 over 2 square root of x. Right? If you're not sure, you can try using the half, and then goes down, and then minus 1, and then you get the result. Okay, so if we take this, we get that this is going to be this. Okay? Now imagine if this is another function, which is g. So we take it down and write the whole thing here. So write down this. And then multiply with the inside function, which is x squared plus 1, but the derivative. Okay. So we can write, perhaps we can write like this. So we get so you could think the ddx of the composite function so this one is the outside function, this is the inside. So it will resulting in f prime g of x and then g prime of x. Okay. Let's try another one. Okay, let's try another one, just to give you some context how to apply this.
Okay, if I have this sine x and then square,
What will be the f prime?
what will be the f prime? First, you could think the outside function is the one that having squared, right? And the inside function is sine x. It's I think obvious from the structure, right? So the outside function is just normal squared functions, x squared functions, right? So you could derive that, becomes 2, and then write the whole thing. Okay? So we can write
2 and then sine x and multiply the inside function, but you need to derive that. Okay? Which is we can write 2 sine x cos x. Or if you want to simplify, this becomes sine 2x. Okay? Let me just make sure that we are clear on this. Let me give you another one. Okay, this is all simple for the examples. Okay, because
if you think that this is a composite, the composite can be more than 2. It can be maybe f, and inside is f, and then maybe many functions. But the rules stay the same. Every time you have a composite, you start layer by layer. You start from the outside, and you have the inside one, derive, and it still have the inside one, and then you need to derive that, until you get into the inside, the most inside one. Okay.
Let me give you another simple examples to see the process. So if f is 5 minus 6x with power of 5, f prime will be,
I think similar to this one. Right? So 5 go here. We write 5 minus 6x with 4, right? And then multiply with the inside function, which is 6 and negative 6, right?
so this will be 5 and this will be 4. And let me write one by one. So this is ddx of this 5 negative 6x. So this one will be, and this is negative 6, right? So we can write negative 35 minus 6x with power of 4. Okay, any questions first?
Any questions? No? Yeah. Which one? Oh, this one? This cosine? Derivative of sine.
Okay, before we end, please scan the QR code for attendance and some feedbacks.
Yeah.